All right. I'm assuming this is the first video you're watching for my Math 142 college math class, and which means you found the videos, which is a good thing. I just wanted to, before I got into the lecture, just say a few things. I tend to be a long talker, so hopefully these few things don't turn out to be more than a couple minutes, because I shouldn't. So anyways, my name's John Grimma. I scribbled it down here, and you can call me Mr. Grimma if you care to, or call me John if you're comfortable doing that. I'm completely okay with either. As you watch my videos, I hope that it's kind of an interactive activity, and you should definitely have paper and pencil handy as you go through and watch my videos, because there's going to be a lot of times where I do a problem and I ask you to do a problem, and so you should have definitely paper, pencil, or pen. It hardly matters in this class so much. You don't have to use pencil, and you should have a calculator around. For most of the class, any calculator that you own will be fine. A calculator that either adds, subtracts, multiplies, and divides will be enough. So just a basic checkbook calculator will be enough. There are 3 sections that we do. There's 28 sections of material that we cover, and in 3 of the sections, all in chapter 3, you need a calculator that's specifically a TI-83 or a TI-84 calculator. Not so much for the graphing. We don't do any graphing in this class. But for doing something that you do in statistics called standard deviation, this calculator does. And for doing money kind of problems, like computing car payments and computing balances in savings accounts, this calculator has some pre-programmed capabilities that we'll exploit just to make the math a little bit easier to do. I don't want you to buy this calculator because it's a $100 calculator. You don't have to buy anything for this class in terms of the book. That's all free. That's all on my webpage. But you can rent this calculator if you don't have access to borrow one, or if you don't have a kid that owns one, or you don't happen to own one. And to rent it, it costs $20. And if you want to rent it, you should rent it earlier in the semester rather than later. The school runs out of them at some point. And to get a calculator, you need to go to the cashier's office, located in the C building at GCC North. If you know what the C building is, it's not that big inside. It's kind of in one of the corners in that building. So you want to have this calculator early in the semester, or just have a way that you could get this calculator. For, like I said, we do 4 chapters this semester, chapters 1, 2, 3, and 4, and for only chapter 3 do you need this calculator. So you can get by most of the semester with either no calculator or a really primitive checkbook calculator. Just in case you haven't been to my website, I'm going to show you how to get to my website. There's always a link on Canvas to my website, and if you don't want to go through Canvas, you can just type my name, if you remember what that is, on Google, and I think I'm the first name that comes. My website's the first thing that comes up. So I'm going to go do that, and I'm just going to kind of go show you what's available on my website for this class. So I just went to Google and typed my name, John Grimma, and the very first thing that comes up is supposed to be me, so hopefully it does, and it did. And then when I click on the website for me, you get to my main website, and first thing, anytime you get to my main web page, you should look on the announcements, which I tried to scroll to, and there'll be an announcement for Math 142 always up there, and the announcement will basically tell you when the next test is and when homework is due. If you come to class on the first day, I'll talk about homework and the benefits of doing homework. So always peek at the announcements, and then the link for Math 142 or Canvas. You might use the link for Canvas every now and then, but the link for Math 142 is the one that we'll use most. We're starting with Chapter 1 right now. If you clicked on the link that said video for Chapter 1, you'd get access to this video. Since I'm just recording it now, there's not going to be anything when you click on the video link, but when I clicked on the video link, now it's blank. It's not there because it's not recorded yet, but it'll be there eventually. Eventually, I'll get it there. Mostly when I do lectures, everything that I lecture about or on is under the problems and answers link. So if I click on the problems and answer link, you'll get this section and all the sections in this chapter. There'll be documents there. Eventually they're going to be PDFs as opposed to Word documents. Right now they're Word documents because I'm still editing them. But if you click on this link, you'll be able to find the lecture material for every chapter, you'd think. Of course, now it's not working. Wonder what happens here. Well, it's not linking to the right thing. So let me turn this out. Let me find it. It will link to the right thing eventually. Well, let me get there and then show you what's going to come up when it works. I thought I checked this before I came here. I guess I checked that the links were working. Eventually, you'll get to a link that looks something like that. You'll click on the link for section 1.1. No. Really? Oh, it's wanting to save. Sorry, I don't know what the heck I'm doing this morning. Save as. Really stumbling here. Let me recalibrate again. And make you watch my computer work. Sorry about the glitch here. All right. Back again. Live. Now let's hopefully this thing over there it is. So you'll get a document that opens, and within that document, every single thing that I'm going to have displayed on my video is going to be within this document. In fact, I'll just go through this document kind of in order, and in the document essentially is kind of the outline of the lecture that I'm going to give, and then within the lecture we'll have problems, and all the homework problems that you're going to be asked to do are going to be in this document as well. As you watch me go through the video, I'll lecture on theory a little bit, and then once we get to a point where we have enough theory to do some homework problems, we'll do some homework problems. And within the video, I will do every even-numbered homework problem. The hopes would be that after I do an even-numbered homework problem, that you would pause the video and do the odd-number homework problem that goes along with it. So eventually in this video for section 1.1, I'll do problem 2. I'll probably have displayed both problem 1 and problem 2 on the same screen, and I'll say, I'm going to do problem 2 right now. If you don't need to watch me, pause the video and you do problem 1, and then bring the video back up and we'll keep going. Every time you do an odd numbered problem, it's important to check your answers. And to check your answers, if you just go to the very end of the document, at the end of every section, I have all the answers written. So when I scroll down to the end of section 1.1, at the very end of it, there's the answer to every odd problem. So you should, after you do a problem, check your answer. You don't have to print out anything while you're watching the video because everything's going to be displayed on your computer screen. But if you wanted to print out the answers might be nice because the answers won't be displayed on your screen. So if you want to do a problem and check it and not have to go, not have to flip out of the video, go back into the document, then if you had the answers in front of you, that would be probably all you need. That's the bulk of the resources that's available on my website are the link to the videos that you're going to be watching now, and all the lecture notes, all the homework problems, along with answers are all contained in one kind of document. If you do a problem and you don't get an answer that you're happy with, then you can click on the solutions document. And in the solutions document, what it's going to have is every single odd number problem worked out the best I can work it out. So with as much explanation as I think will help you understand the problem. So if you do a problem and you get the wrong answer, it could be that I have a mistake. So if you get a wrong answer and you can't figure out how to make that answer correct, then send me an email, because I wrote this stuff, and it takes usually about 4 semesters for all the mistakes to kind of wash out of it. So, but if you clicked on the solutions link, then a document will come up, and that document should have every single odd numbered problem, how I got my answer explained, and that might be enough to get you, unstuck, or it might be able to help you really realize that I have the mistake and it's not your mistake. So that's a link that you might never look at. You might be able to go through every single problem this semester, and with my lecture, it might be good enough for you to solve the problem. But if it's not, I have solutions that are all typed up, are written up if they're hard to write. All right, so back to my web page. So that's kind of everything you're going to need most of the time. So videos that you're watching right now, problems and the answers, which have all the lecture information with the problems that we're going to do. I'm going to do the even problems, you're going to do the odd problems. You should check all your answers. There's solutions if you get stuck on any particular problem. And then there's something that says in-class problems. Mostly my Math 142 is in a hybrid format. And on class days that aren't test days, the stuff that I'm going to do in class, or that we're going to do in class, is going to be under that link. That's probably already more than you probably wanted to hear from me, so let me just start lecturing right now. On the first day of class, I'll restate all this so that if you miss something and you can't ask a question to the computer, I'll hit that again when you come to class the first day. All right, so back to the class now, into the lecture. So if anything right now, if you took the time to print out the answers from section 1.1, that's probably not a bad idea. And now for the rest of the lecture, I'm going to just take the time to do every single odd numbered problem, every single even problem in this section. It turns out that in Math 142, especially in the first chapter, there's a lot of just terminology and just words that we use that you might not be that familiar with. So I can't jump right into problems. Just about every section this semester that I've written, there'll be a little bit of a lecture that's written up before we get into the problems. I wrote all this stuff up, and I hate when teachers just read their lecture, so I probably won't just read this. I'll just kind of paraphrase it. You're more than welcome to read it word for word if you want. Quite honestly, you could just listen to what I say, and that should be enough. I should paraphrase and say everything that's in my notes. Maybe better than I wrote it. Who knows? So I'm just jumping into it now. So for the first section 1.1 is an introduction to sets. If you went to grade school in the 70s, you got real familiar with sets, because sets were quote unquote the new math that they introduced in every math class between 1st and 8th grade. But I think if you went to grade school in the 90s or the 2000s, they've kind of lost favor, and so you might not be that familiar with sets anymore. So a set is just a collection of objects, and each object is called an element or a member of the set. And sets, when they're named, are usually named with capital letters. That's a good definition if you already know what a set is. A horrible definition if you have no recollection of or no idea of what a set is. So I've written some problems just to get us kind of familiar with set terminology and what sets are. So first example, let A be the set of integers between 2 and 5 inclusive. So there's lots of words in here that you might not be familiar with. Set we're definitely not familiar with yet, but that's what we're getting familiar with. Integers are numbers that are positive and negative that don't have fractions or decimals. So I'm listing the positive and negative integers, and I'm putting ... to say the numbers continue. So to the right, 5, 6, 7, 8, and 9 are integers. To the left, -4, -5, -6, -7 are integers. So integers are basically just numbers without decimals or fractions, whether they're positive or negative. So between, well, that's not a new word, but inclusive may be. So
I'm going to list the set of integers. I'm going to call it set A, so I'm going to write A equals, because it says that A is its name, and I'm going to write the integers between 2 and 5. So the integers between 2 and 5 are the numbers 2, 3, 4, and 5. And in our class, if we see the word inclusive in a description, it means it includes the first and the last number mentioned. Had it said between 2 and 5 exclusive, that would mean it would exclude the first and the last number mentioned. So exclusive, you don't, that doesn't even look like exclusive. Exclusive means you don't include the first and the last number mentioned. I'll say, well, just don't include I'll call it endpoints just to save some room here. So these are the integers between 2 and 5, including the 2 and the 5. When I glance at that, it doesn't look to me, somebody that reads mathematics, like it's a set. And in my instructions here, I said place the elements, 2, 3, 4, and 5. The objects that are in set A can be called elements, or they can be called members. Elements is probably more common. It says place them in set braces. Set braces are just these squiggly braces, like that. So there's an answer to the first example. I've created a set, I've named it A, that's actually an equal sign, and I've put the elements of A, the numbers 2, 3, 4, and 5, in set braces. That's the perfect answer for the first example. It would be completely okay if I scrambled the order of the elements. So if I wrote A equals 2, 4, 5, and 3, that's equivalently correct. Two sets that have the same elements written in a different order are considered equal to each other. And the order that you write the elements of a set in isn't important, but it's nice if there are numbers if you write them in ascending order. But it doesn't. You don't have to. So that's everything that completed set 1. And completed the first example, and I have some more words down here, and maybe I'll just kind of read through them to make sure I kind of hit everything. So one of the things is we're introducing the concept of set, and to be a set, you're just a collection of objects, and the objects could be anything. The objects could be, football teams. They could be books. Mostly for our class, when we create sets, the objects are numbers or letters. And so here, this is a collection of objects, the objects being numbers. So like I said, this question, let A be the set, write the elements down, it implies that A is a set. And A is a set because, first of all, it's in set braces, and what's inside it are objects. And the rest of the stuff down here, I talked about integers inclusive already. There's a better picture of what integers are, and there's a better picture of what exclusive are. Yeah, that's got to be good enough. Oh, and I even did the same sort of thing. So all of this is just rehash of what I said as I did the last. Look at that, I even came up with the same odd ordering. Isn't that because when I make up problems, I think like I think. What came up. I probably wrote this 6 months ago, but I still came up with the same example, and I didn't even look at this page before I entered it. This is wrong here. This should be 5, 4, 3, 2. So as long as you have the numbers 5, 4, 3, and 2, or 2, 3, 4, and 5, you have a correct answer. All right, move on. The next thing, had my example had the words exclusive, which I talked about exclusive, the 2 and the 5 wouldn't be included. So between in mathematics, you have to look more than just the word between. Anytime we see the word between in our class, we're either somewhere in that problem going to have the word inclusive or exclusive. And the next example is going to be the same problem with the word inclusive changed to exclusive. So if I wrote let A be the set of integers between 2 and 5 exclusive, then I'm not going to include the 2 and the 5 in my listing. And then this example says list the elements of set A, place them in set braces. So the integers between 2 and 5 are the numbers 2, 3, 4, and 5. Inclusive, I include the 2 and the 5. Exclusive, I exclude the 2 and the 5. So for this example, my set A is just going to have the numbers 3 and 4. Not sure what's coming next, but so here's another example that will help with the homework below. So let's see. Oh, yes, it will. So here's a new set B. So when I name it, I'm going to say B equals. And B is what? It's the set of solutions to the problem x plus 5 equal to 8. Well, in order to figure out the elements of set B, I have to be able to find the set of solutions to this problem. And to find the set of solutions to that problem, well, I just solve it. We're not going to do a lot of algebra in this class. I don't think we're going to factor a single time. In fact, I know we're never going to factor. And at most, we might do some problems where you have to solve with square roots, or simple problems like this where you have to solve by subtracting or dividing. In this particular problem, the equation that defines set B has only one solution. It's the number 3. So the set B just has one element, the number 3. So B is the set of solutions to that. I found the solution, the only solution to that, which was C, which was 3. Now I'm going to write set B. I'm going to list the elements of set B, which is the number 3, and I'm going to place them in set brackets, or set braces. So the answer to this next example, B is the set that contains just the number 3. Now we get to the homework part of the lecture. And most of the time throughout the semester, I took the time to write both the even and the odd numbered problems that have the same skills together. And like a moron, I made 1 and 2 exactly the same. So let me change my numbers here to make 2 different, and I'll change it if you print it out. So problems 1 through 8 solve just like the 2 examples or the 3 examples that I did. I'm going to list the elements of the set, and I'm going to write my answer in set braces. So both problems 1 and 2, the problem 1 that's not going to change, and the problem 2 that I just changed, so it's not exactly the same as number 1, give me a set, and it's called set A. Oh, they're not the same. Idiot. I just didn't read close enough. I can leave it 1, and sorry about that. And I glanced at it and didn't read them completely, so I wasn't an idiot when I wrote this. I'm an idiot more often than not, but not when I wrote these 2 problems. So as I read through problems 1 and 2, I thought they said exactly the same thing, but I didn't. I missed the word even and odd. So when I go to do my problem 2, first of all, A is the set of odd numbers between 1 and 10. And to be an odd number, you have to be an integer. You're not going to have, like 3.5, we wouldn't consider that even or odd. So if I list all the numbers between 1 and 10 that are integers, because to be even or odd, you have to be an integer. For my problem number 2, these are all the numbers between 1 and 10. But I only want to consider odd numbers in my problem. So immediately I know these numbers can't be part of my set because those are even numbers. When you go to do problem 1, if you listed all the numbers from 1 and 10, you'd have to cross out the odd numbers because your set is only asking you to list even numbers. Now I have to ask myself, I know all the numbers not counting the 1 and not counting the 10 are definitely included because these numbers 3, 5, 7, and 9 are between 1 and 10. I look to figure out whether I'm allowed to include this 1 or not to the word inclusive. If it said exclusive here, I wouldn't include the 1, but because it says inclusive and the first and the last number, if they fit the definition of the set, are included. I'm not going to include the 10 because it doesn't fit the definition of the set. The set only includes odd numbers. So for my answer to number 2, the set's going to contain the numbers 1, 3, 5, and 7. It's not going to, and 9, idiot, and 9. It's not going to contain the number 10, even though it's mentioned in the definition of set A. It doesn't fit the criteria of being an odd number. So you should be able to do the same thing for number 1 and have an answer that looks similar. So 3 and 4 is, well, exclusive. Basically, I took the questions from 1 and 2 and changed the words to exclusive from inclusive. So again, both problems 3 and 4 are mentioning even or odd numbers, which automatically means I'm not dealing with decimals or fractions. So if I listed all the numbers between 1 and 10, all the elements of set B have to be within that list. And for my problem, I'm going to scratch out the even numbers because I'm only asked to include odd numbers. So those are the odd numbers between 1 and 10. And now I have to figure out if I'm allowed to use the boundary numbers or not. The word exclusive means I can't include the 1 nor the 10 in my answer. The 10's already got excluded from my answer because it wasn't an odd number. Now the 1's got to get excluded from my answer because the 1's not exclusive, and it's not part of the exclusiveness because the numbers between 1 and 10 exclusive are 2 through 9. So my answer for question 4 is going to contain the numbers 3, 5, 7, and 9. Five and 6 basically are the same problem. To get my problem 6 done, I have to solve the problem that's given. The problem that's given in problem 6 is x minus 4 equals to 9. And I'm going to solve that by adding 4 to both sides. The answer is x equal to 13. So the solution to this problem is 13. And when I go to write my answer to number 6, I'm going to write A because that's the name of the set. I'm going to write an equal sign. And then generally when we're listing the elements of sets, we put those elements inside set braces. And the only solution to this is the number 13, so there's only one element of the set A. Okay, so 7 and 8 require you to have some knowledge. Hopefully you know the ice creams that make up, the flavors of ice cream that make up Neapolitan ice cream. If not, you can research it on the web. And then I made mine easier, but mine's a nuisance to write. So B is the set of days of the week. I guess we'll do it in English. I'll start with Sunday. And then Monday. And then if we start abbreviating because we don't want to write everything, I mean, it gets, it's silly. Well, it's not an English class. So I'm running out of room here, so I'm going to use Wednesday, Thursday, not even putting decimals for all my abbreviations, Friday, and Saturday. That would be more than enough for me. I'm never going to take off for a spelling error or any sort of grammar error. So if you abbreviate and you don't put a period like I did for Wednesday, it's just not that big of a deal for me. And if your writing is at least as legible as mine, that would be nice. My writing sometimes isn't that legible. I apologize for that. One thing you could be nice to me when you're doing your test, if you're a really small writer, if you can write just a little bit bigger than you normally do, because my eyes are getting old, and sometimes I just can't. Some students, they write with they write really small and they write in pencil. It's, I almost need a magnifying glass to read it. So if you can write a little bit bigger, if you're a small writer, I'd appreciate it. So that's the first 8 homework problems. The next group of homework problems, we need some new concepts. And I like to kind of break my lectures up into, I introduce a concept, do some problems, introduce a concept, and do some problems. So those 8 problems all fit the concept of what a set was. The next concept is something called well-defined. And so well-defined is kind of a touchy-feely concept because there's no precise definition. A set is well-defined if any informed, objective person can decide whether a given element is in a set or not. So it's a weak definition at best. If I was asked if a set is well-defined or not, and in the description of the set, if I saw words as good, bad, nice, then it's probably not well-defined. So the next few examples, I give a word description of a set, and I ask you, is that set well-defined? So my first example, set M probably standing for months, is a set of months with more than 30 days. Is this well defined? It's well defined. If I give you a month, you can clearly say, objectively say, yes, this is in the set, or it's not. So if I gave you the months January, if you didn't know January had 31 days, you can look at a calendar and figure that out. So January would belong in the set. If I gave you the next month, February, you'd say, well, no, February doesn't belong in that set because it has less than 30 days. If I gave you March, does March belong in the set? To belong in the set, you have to have more than 30 days. March only has 30 days. March has 31 days, doesn't it? So March would include in the set. April has 30 days. 30 days isn't more than 30 days. April wouldn't belong in the set. So there's no ambiguity in the definition. If I give you a month, I can tell you whether it belongs in the sets or not. These months, January, March, May, July, August, October, and December belong in the month. I didn't need to list the elements. Notice I didn't take the time to put them in set braces. The question is the set well-defined or is it not well-defined? For this, I'm going to say the set is well-defined. If I got lazy for my answer, I could have just said yes. The question, is the set well-defined? That's really a yes or no question. So for my answer, it would have been completely fine if I just said yes. That would imply the set is well-defined. So next example, let C be the set of good cell phones. And for me, words like good, bad, and nice usually means undefined. As I write this right now, I have an iPhone 5. And at some point, that's going to sound silly because it's going to be an antique. But I'd call that a good cell phone. But somebody else that likes Samsung Galaxies might say that's a crappy cell phone. They might not call it a good phone. Or somebody that has which is new now, the iPhone 6S, might say, well, your phone's no good because it doesn't do whatever this does. But I've got buddies that have flip phones and they think their phones are good because they're good for what they do. So it's ambiguous. Different people might call one phone good, why another person might not. So the set is not well defined because it's completely dependent on who's asked whether a cell phone is good or not. So for my answer, I wrote the set is not well defined. You could have just said no for your answer, and that would be sufficient to answering the question, is the set well defined? So 9 through 16, we just have to go through the sets and figure out if they're well defined or not. Again, they're well defined if you give me something that might fit in the set, and if everybody essentially would come up with the same answer that's objective, then we're good. So for your question 9, the set of goofy dogs, that's probably not well defined. Goofy isn't one of the words that I mentioned, good, nice kind of words, but goofy is probably also a matter of opinion. So I'd say 9 is probably not well defined. There's no work to do. It's not well defined, and I'll be done. And for my set B in number 10, the set of GC students whose GPA is 3.0 or greater, that I probably can do. I probably could ask some of the computer guys on campus to give me a printout of all the GCC students ranked by GPA, and I can find every student whose GPA is 3.0 or higher. So for my number 10, I'm going to say it is well defined. If I just said yes, that would be sufficient, but I'm going to just give an answer that is fine. Yes would be fine, is well-defined, or well-defined would be fine, or for your answer, no or not well-defined would be fine as well. Okay, my number 12 has the word good in it, and good is very subjective. Some students that I consider good students might not even consider themselves good students. So good is definitely a matter of opinion. So for my number 12, I'd say my answer is it's not well-defined. For your number 11, I hate to give away all the answers, but yours is well defined, because if you give me a number, like if I give you the number 3, is it square 16? Well, 3 squared is 9. 16 doesn't belong in the set. If I give you the number 4, what's 4 squared? 4 squared is 16. It does belong in the set. So no matter what number you give me in part D, I can square it and tell you whether it belongs in the set, because it only belongs in the set if its square is 16. So your 11 is going to be well defined. For my number 14, the set of Great Lakes, Ontario, Erie, Michigan, Huron, Superior, that's a well-defined set, because even if you don't know what the Great Lakes are, that information is known. You can get that information, and it's not going to be debatable whether a lake belongs in the set of Great Lakes. You know, if I gave you Lake Mead, it's not considered a Great Lake. You might think it's a Great Lake just because you like going to it, but it's not, quote unquote, one of the Great Lakes. Those are up in the Midwest. So for mine, this is definitely well defined, and then I'll let you figure out if 13 is or isn't well defined. 16 feels so much like a problem that I already did. Sorry that the repetition here. I think it's worded slightly different, but for my 16, it's definitely going to be not well defined. The set of good smartphones, I think I already had that discussion. That's definitely not well defined because good is really a matter of opinion, and your 15, it seems like an opinion-y thing too. You know, I think Phoenix has a nice climate, but my dad doesn't think Phoenix has a nice climate. He thinks it's just too hot here. So that's probably 15 is probably not well defined. All right, next concept, then we'll get some problems. So the next concept is finite or infinite sets. So finite sets, it's possible to list every element of the set, where an infinite set, it's not. So if I give you this set A, I didn't list every element of set A. I put ... to say the pattern continues. These ... dots are called ellipses. And the pattern continues but stops at 20. Is A finite or infinite? Well, if it's possible to list all the elements of A, it's finite. If it's impossible to list all the elements of A, it's infinite. Well, I took the time to type all the elements that are implied by the ellipses, and there's only 20 elements. So since it was possible to write down all the elements of A, the set A is finite. I don't want you in this section to write down all the elements of a set. That's silly. Just in your mind, understand all the elements of the set, and if it would be possible to list them all down, it's considered finite. If it's impossible to list them all down, it's infinite. So the next set I have is the set B, and this set, it has the ellipses that mean the pattern continued, and it doesn't have an ending number. It means the pattern continues and doesn't end. So I can start writing the numbers that form the pattern, but I'm never going to get done because this ... means the pattern goes on forever. It goes on past 1,000, past the millions, past the billions. It goes on forever. So no matter how much I write, the set B is going to be more than I can write. So it's impossible to write all the elements of set B. So set B is infinite. So now we've got some words that I know because I teach math that you might not know. So next example, is this set infinite or finite? The set A contains the factors of 10. What does it mean to be a factor of 10? That means those are numbers that divide evenly into 10. And so the 1, 2, 5, and 10 are the factors of 10, because 10 divided by 1 is 10, 10 divided by 2 is 5, 10 divided by 5 is 10, 10 divided by 10 is 1. Numbers like 3, 7 aren't factors of 10 because when you divide them by 10, they get a remainder. And that like 2.5 wouldn't be considered a factor of 10, or 2.25 wouldn't be considered a factor of 10. Even when you divide 10 by 2.25, you don't get a remainder, but by factors, they have to be, I'll say positive integers. Maybe might also consider negative integers, but whether if I'm only considering the numbers 1, 2, 5, and 10, and if I allow them to be negative, I still only have 8 factors of 10. So it's possible to list all the elements of set A because there's only 4 positive factors of 10, 4 negative if you want to include the negative. So there's 8 factors total if you count positive and negative, 4 if you only count the positive. So this is a finite set. It was certainly possible to list all the elements of the set. The next problem, the set of multiples of 4. Notice I didn't call it set A. I didn't name it, but that doesn't matter. I didn't say the set A, which is the multiples of 4. What does it mean to be a multiple of 4? Any number that 4 divides evenly into. So I started listing them. 8's a multiple of 4, it's 4 times 2. 12's a multiple of 4, it's 4 times 3. 16's a multiple of 4, it's 4 times 4. 20's a multiple of 4, it's 4 times 5. This list goes on. 24 would be another number in the list, and then 28 and 32. So multiples are different than factors. the list of multiples go on forever. So it's impossible to list all the multiples of 4. I listed, 5, 6, 7, 8 of them, but I wasn't even close to getting all the multiples of 4. So this is considered an infinite set. So now some homework problems. You don't have to list the factors to know whether it's finite or infinite, but you can. Factors are going to be finite, multiples are going to be infinite. So for me, the factors of 24, 1 goes evenly into 24, 2 goes evenly into 24, 24 divided by 8 is 3, 4, 5 doesn't go into it, 6 does, 7 doesn't, 8 does, 9 and 10, 11 don't, and 12 does, and 24 is a factor of itself. Those are all the factors of 24, all the positive ones, so there's 8 of them there. If you count the negatives, you get 16 of them. The answer to number 17 and 18 is when you're asked to find factors, that's a finite set. When you're asked to find multiples, it's an infinite set. And again, if you wanted to list the factors of 12, there would be 1, 2, 3, 4, 6, and 12. There's 6 of them. 12 if you count the negatives. That's a finite set because I can list them all down. So for 19 and 20, the multiples of 5, 5, 10, 15, 20, and they go on forever. I don't need to take the time to write nice set notation here. I realize that that's an infinite list, and so my answer to problem 20 is this finite or infinite? I can't really say yes or no. It's not a yes or no question. It's an either or. I need to give the one that's true, and it's the infinite that's true for number 20. '21 and 22 are a little bit different. Mine's a little bit harder. The sets of multiples of 4 that are greater than 10 and less than 50. So if I list the multiples of 4 and I get up to 50, I don't need to go any further. So in my description for this set, I need the multiples of 4 that are greater than 10. So I'm not going to include the 4, I'm not going to include the 8, because all those are multiples of 4, they're not greater than 10, so they don't fit the definition of the set. And less than 50. I don't include any multiple of 4 bigger than 50. So 52, 56, 60, 64, which are all multiples of 4, but they're not less than 50. They're not going to be included. There's infinitely many multiples of 4, but the ones I'm considering in problem 22 are the numbers 12 through 48 that are multiples of 4. So this is a finite set. So 22, because of the extra words attached after the multiples of, because I'm only looking at specific multiples of 4 and not every multiple of 4, this becomes a finite set. You could do something similar for your number 21. You can list all the multiples of 4 and then cross out the ones that don't count. And now it makes a difference whether we're considering positive or negative, because I'm just going to count the positive multiples of 4. So consider this a set of positive multiples of 4. If you start considering negative, then you get a different answer for number 21. So again, for even and odd, I'm only considering positives. And for me, the set of odd positive integers, let me see, positive integers, so 1, 3, 5, 7, and 9, they're all odd, and they're integers, and they're all positive. I can keep going, 11, 13, 15. I can keep going because there's still more odd positive integers, 17, 19, 21. I still could keep going. In fact, I can never stop this, so I can just go ... The pattern continues. This is an infinite list. It's only counting odd integers that are positive, but nevertheless, I tempted to start writing the list, and every time I got to a point, there was still more. That's always going to be the case. It's going to be impossible to write all these. This is going to be considered an infinite set. Okay, the next concept is the empty set. The empty set doesn't come up a lot in this chapter, but it comes up a few times. And an empty set is a set that has nothing inside of it. And a 0 with a line through it, that's a symbol that means empty set, which means a set with nothing inside of it. And it's the only set that gets that special notation. Most sets, when we're trying to list the elements, we would just write the squiggly brackets. This also means an empty set. If you write the set braces and put nothing inside of them, that's an empty set. That's a set with nothing inside of them. So these two symbols mean exactly the same thing. When I see that or that, I think a set that has nothing inside of them. So here's an example of an empty set. The set A of months in the year where the average high temperature in Phoenix is less than 10 degrees Fahrenheit. That never happens. There's no month of the year that the average temperature in Phoenix is less than, average high temperature is less than 10 degrees. So A is the empty set, or the empty set. All three of these, to somebody that reads mathematics, would say set A equals the empty set A equals the empty set A equals the empty set. Oh, now more notation. This symbol, which I have a hard time writing, this means is an element of or is contained in. This symbol means the element. So if I see an object to the left of a element, not in a set braces, but just an object or an element itself, and then a set name, this means in the list of set A, in the elements of set A, that 5 would be part of this. So like if this was the set A is the numbers 1, 2, 3, 4, and 5. If this was the set A, I would read this as 5 is an element of A, and this is a true statement because if I look at the elements of A, 5 is in there. If I put a slash through the element symbol, it means it's not. And so this would be true. Saying 6 is not an element of A, for that set it would be true. So these for this set A, these are true statements. 5 is an element of A because in the listing of A there's the number 5. 6 is not an element of A because in the listing of A there's not a number 6. Okay, true or false questions. Are these true statements? So first statement, I have given the set B has the numbers 1, 2, 3, 4, and 5. Is 1 an element of B? This is going to be true because inside the set of B has its elements. B has the elements 1, 2, 3, 4, and 5. 1 is part of it, so it's true. This is, well, I'm doing your question. It's just an example. Okay, so I'm not doing a homework question yet. So this one is not an element of B. Well, that can't be true because since it's true that 1 is an element of B, this is false. This says 1 isn't in set B, but 1 is in set B. So this says 1 is in set B, it's true. This says 1 is not in set B. Well, 1 is in set B, so it's false. For these two, one is going to be true and the other is going to be false, always. If you take the same element and say, is it an element or is it not an element, then one's true and one's false. Here, because 1 was an element, saying 1 wasn't an element was false. For these two, 8 is not an element of B. That's true because in the list of B, 8's not in there, so that's a true statement. This one says 8 is an element of B or 8 is contained in B. Well, 8 isn't contained in B, so this is false. So any element it either is or isn't part of the set. If it's part of the set, then this is true. If it's not part of the set, then that's true. And then the opposite is always false. Might have rushed through that a little bit quickly, but we'll get some of this in the homework. Natural numbers is a set that comes up a lot in this class, and a lot in chapter 1, should I say, and later on in the class it doesn't come up. So the natural number of a set denoted with the letter N, sometimes a small n, sometimes a capital N. I'm consistently inconsistent with using small and capital N's because it doesn't matter. The set of natural numbers are integers that are greater than 0 that don't include 0. So this is the set of natural numbers. And so I could say N is the set of natural numbers. And the more I think of it, that I won't be inconsistent about. I'm going to use a capital N to represent the set of natural numbers, and it's an infinite set, so I need the ellipses or the dot, dot, dots in my answers. So that's going to come up a lot in chapter 1, just knowing that if I see integers, I'm not allowing decimals, I'm not allowing fractions, but I'm allowing 0 and I'm allowing negative numbers. So integers include 0 and negative numbers. Natural numbers don't include negative numbers, they don't include 0. Another concept, one thing I don't like about chapter 1 is there's so many words and concepts that it just feels the lectures feel kind of just not fluid, because I'm always stopping to define a term. But I don't want to define all the terms and then do the homework, because you'll forget the terms before we do the homework. So I do all the terms that we need, and then I do the homework that relates to those, just to keep you from forgetting. And the next thing, the next term is cardinal number. Cardinal numbers only work for finite set. I wouldn't ask you to find the cardinal number of that set because it's infinite. It's just the number of elements in set A. And cardinal numbers, I use this symbol for. A small n meaning the number of elements, and then the set name in parentheses, and then to the right of it I'll write how many elements are in the set. So here's an example. Find the cardinal number of set A, where A is the set 2, 3, 4, 5, 6, and 7. Well, A has 6 elements in it, 1, 2, 3, 4, 5, 6 elements in it. Thus, the cardinal number of set A is 6, because the cardinal number of a finite set, there's no such thing as a cardinal number of an infinite set, is a number of elements in the set. This set A has 6 elements, so I'm going to write symbolically nice. The number of elements in set A is 6, and using the symbol, small n followed by a parentheses with the set name, that stands for the number of elements or the cardinal number. It wouldn't be wrong if I said A has 6 elements. That would be a correct answer, written probably not very nicely. Or it wouldn't be wrong to say the cardinal number like this, the cardinal number of set A is 6. So all of these would be correct answers. This is the nicest correct answer of the question, what is the cardinal number of set A? To somebody that reads mathematics, they'd say the cardinal number of set A is 6, or A has 6 elements. Okay, another example. Find the cardinal number of A, where A is a set of natural numbers less than 8. Well, if I consider the set of natural numbers, the set of natural numbers starts at 1, and it goes on forever. But in this one, I'm only considering the natural numbers less than 8. So I'm definitely not including 9 or 10 or anything bigger. And because it doesn't say less than or equal to 8, I'm not including the 8. If it said less than or equal to 8, I'd include the 8. But 8 is not considered less than 8. So the set A that we're referring to here only has the numbers 1, 2, 3, 4, 5, 6, and 7. Set A has 7 elements, so in my answer, I'm writing the symbol for the cardinal number of A, which is 7. I could do in words, say the cardinal number of A is 7. If you just wrote the number 7 down, I'd live with it, but it's like the worst possible answer. This would be an okay answer, but not that good. It's surprisingly predictable a way a student writes an answer, what kind of grade they're going to get in the class and what kind of grade they're going to get in the test. It would be like if this was a test question and you wrote 7 for your answer, I would give you credit, and it would surprise me if a student that was lazy and didn't learn the proper symbol or didn't learn a sentence that went along with the answer. It would surprise me if this student winds up getting an A on the test. It would be almost shocking. It turns out that the students that don't take the time to learn the minute detail in this class, they get tricked on the problems that have little tricks. I don't try to make tricky questions ever, but for students that don't take the time to learn the material like it needs to be learned, they're going to get caught up on things and think things that are tricky, where a student that takes the time to learn this won't even find it tricky. They'll go through every one of my tests and get an A, whereas students that are a little bit lazy, they'll not get A's just because they're lazy, not because they can't learn the material. If I had to guess, not that it matters right now, but usually about 30 students sign up for my class, because 30 is what we cap our enrollment on. By the end of the semester, usually 4 students drop for whatever reason. They find out they need a different class, or their work schedule changes, or they just don't like watching these videos. So of the 26 students that stay in the class, I guess I'll give 14 A's, maybe 15 in Math 142. So it's a pretty easy class to get an A in if you do the work. If you don't do, you don't need any special mathematical ability at all to get an A in this class on top of that. But if you find yourself being lazy and you do the work, you might be one of those students that doesn't get an A. Okay, another group of homework. So we're listing the set and we're just finding the cardinal number of the set. So it's important to look at the instructions. So listing the cardinal number. So when I go to do problem 26, I want the cardinal number of set B, so my answer is going to have an N and a B for the cardinal number of set B, and then an equals, and now I have to figure out the numbers that make up the set, and mine is asking for even natural numbers. Yours is asking for natural numbers. So when I list my set, so the natural numbers between 5 and 10 inclusive are the numbers 5, 6, 7, 8, 9, and 10. That would be the set for your set B, but for me, I'm only wanting even numbers, so I'm going to take from this set, I'm going to get rid of the odd numbers. So my set B would have the even natural numbers between 5 and 10. I would be allowed to include the 5 if it was even, but I'm not. My set B has the elements 6, 8, and 10. It only has 3 elements, so my answer to B is going to be the number of elements, or the cardinal number of B is 3. Again, I could say in words, the cardinal number of B, of set B, is 3. So this is probably the best. This is a good but not best, but okay. And this would be okay, but definitely probably the worst answer. So as long as you get the number 3 for my problem, you're fine. And for yours, I think it's going to be the number 6 because you're counting all the numbers 5, 6, 7, 8, 9, and 10. So 27 and 28, I should do 28, you should do 27. After you do 27, you should check your answers. So I want the set of odd natural numbers greater than 2, less than or equal to 5. So again, if I just list the natural numbers between 2 and 5, I'll discount the ones that I'm not allowed. So first of all, I'm only counting odd numbers, so I'm not counting the 2 and I'm not counting the 4. And then for the end numbers, I wouldn't include the 2 anyways because 2 isn't greater than 2. But I already discounted it because it wasn't odd. And for the 5, I'm allowed to equal the 5, so I'm going to include the 5. So my answer to number 28, the cardinal number of set A, is 2. The 2 elements, these are the 2 odd natural numbers between 2 and 5, not including the 2 and including the 5. Okay, so for 30, and you can do 29, I'm writing this I'm writing the set of natural numbers. I'm stopping at 5 because I'm going only up to 5, and I'm including the 5. If this just said less than, then I'd only have the numbers 1, 2, 3, and 4 in my set, and I wouldn't include the 5. When you do problem 29, your numbers that set A defines only go up to 8, but mine go up to 9, up to 5 because I'm allowed to equal to 5. And for my answer to number 30, again, I don't have to list the elements, but it would be hard for me not to get the answer to what the number of the elements of the set are without listing the elements. So I'm listing them. I'm not even taking the time to put them in set braces or writing A equals. I could, but I don't need to. That's not part of my answer. I could take the time to say the set A equals and then put it in set braces, but it's not necessary. All I have to do is find the elements of set A, and I don't need to write set A in such a nice form. Find n of B. Oh, okay, so this is a little bit different question. Find the cardinal number of set B, where set B is listed with those elements. This is an easy question. I'm given set B. I'm asked to find the cardinal number of set B. The cardinal number of set B is the number of elements in set B, and there's 1, 2, 3, 4, 5 elements in set B. So the answer to 32, the cardinal number of set B is 5. So your 31 should be equivalently easy. Getting close to the end here, I sense, because my stack of papers is almost down to nothing. So for my 34, find the number of elements in set D, where D is a set that contains the number 0. That's not the empty set. An empty set, there would be nothing inside that. In my set D, there's one element inside the number 0. So the number of elements in set D, the cardinal number of set D is 1. Oh, right. I forgot about this. I thought this was in the next section. Definition of set equality. Two sets are equal if they have exactly the same elements and the order doesn't matter. So are these sets A equal A, B, C, D, and E, and B equal to set E, D, C, A, and B equal? They're equal because each set has the letters A, B, C, D, and E. They have exactly the same elements. They both have 5 elements. They have exactly the same 5 elements. So these are considered equal. Yes. So the answer, are they equal? Yes, they are equal. Yes. But yes, I think, is what I chose for an answer, so I'm going to write that. I'm just going to do these for yes, no. Because this is a yes, no question. Are they equal? Yes, they are equal, or no, they're not equal. So look at the sets A and B here, where A has the numbers 1, 2, and 3, and B has the letters A, B, and C. Those aren't equal. So the answer is no. It turns out that two sets that have the same number of elements are called equivalent. We'll get that a little bit later, and we don't need that right now to answer this question. Are these set equal? No, they're not equal. And then the next example, A is a set 1, 2, 3, B is a set 1, 2, 3, and 4. They're not equal because B has the number 4 and A doesn't. So to be equal, they have to have exactly the same elements. Oh, there is equivalence. Haha. So equivalent, I almost thought that wasn't right here. Equivalent means they have the same number of elements. So it turns out if sets are equal, they're by default equivalent, but you can be equivalent and not equal. So are these sets equivalent? It's either yes or no. A has 5 elements, B has 5 elements. Since they both have 5 elements, the answer is yes. So equivalent, they could have the same elements, but they don't have to. The only requirement to be equivalent is they have to have the same number of elements. So these two sets are both equal and equivalent. These two sets, they weren't equal, but they are equivalent because they both have 3 elements. So two sets that are equal, by definition, are equivalent. Equal, you have to have exactly the same elements. Equivalent, the same number of elements. These two sets, they're equivalent because they have the same number of elements, but they're not equal because they don't have exactly the same elements. And the last example here, these aren't equivalent because they don't have the same number of elements. A has 3 elements, B has 4 elements, and to be equivalent, you have to have the same number of elements. So these are both equal and equivalent. These are equivalent but not equal, and these are neither equivalent nor are they equal. Oh, determine whether the sets are equal, equivalent, or neither. So these two sets aren't equal because they don't have the same elements in it, but they are equivalent because they have 4 elements each. So for these, they're not equal, but they are equivalent. So the only thing that these two sets are from this list, they're not equal, they are equivalent. I'm not going to say they're neither because they're one of the two. So those are only equivalent. Those two sets both have the letters A, B, C, and D just written in a different order. So are these equal, equivalent, or neither? Well, they're equal because they both have the elements A, B, C, and D. They have exactly the same elements. So that makes them equal. They're also equivalent because they both have 4 elements. If you're equal, by definition, you're equivalent too. If you're equivalent, you don't have to be equal. So those two sets are both equal and equivalent. And then probably the last example before we get to the homework. Set A has 3 elements. Set B has 4 elements. They're not equivalent. And they don't have exactly the same elements because B has an A in it and A doesn't have an A in it. So they're not equal because they don't have exactly the same elements because A is missing the A. They're not equivalent because A has 3 elements and B has 4 elements. So they're not equal. They're not equivalent. So these would be considered neither. The last homework problems, 35 through at least what I think are the last homework problems, they ask the question, are the sets equal, equivalent, or neither? So I'll do 36, you'll do 35, and our answers aren't going to be the same. and that hopefully you can get through that. So for my set, they're not equal because the B is missing the 1. For them to be equal, they both would have to have the same 4 elements. They're also not equivalent because B has 3 elements and A has 4 elements. To be equivalent, they would both either have to have 3 elements or both have to have 4 elements. So my answer to problem 36, are they equal, equivalent, or neither? My answer is going to be neither. Your answer is going to be both equal and equivalent because they're equal. They have both have A, B, C, and D exactly, and they both have 4 elements. So you're going to have both equal and equivalent. 37 and 38. Your 37 is more like my 36. My 38 is more like your 35. Mine, these are equal because they both have only the letters A and B, or elements A and B. And they both have 2 elements, so they're also equivalent. So I get both equal and equivalent, and it's enough just to write the words equal and equivalent. For you, you're going to write neither. 39 and 40 are kind of like each other. So my 40, they're not equal because they don't have exactly the same elements, but they are equivalent because they both have 3 elements. And once I get one of the 2, I'm not going to say neither. So my answer to 40 is going to be equivalent. They're definitely not equal because 1, 3, and 2 is not the same thing as lemon, cherry, and apple. Our 41 and 42 have different answers. Hopefully you can figure yours out. And always should be checking your answers to the back of the book. Mine are going to be neither because this has 3 elements. This has 4 elements. It makes them not equivalent. And they don't even have any elements in common. So they're going to be neither equivalent nor are they going to be equal. So the nice thing about this class is your algebra skills can be kind of wretched, and everything's going to be either something you've seen before or it's going to be completely new, but it's not going to really hinge on your algebra skills. 44 for me, this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. They both have the numbers 1, 2, 3, 4, and 5, so they're equal. And they both have 5 elements, so they're equivalent. And you can do your 43, and then hopefully you've checked all your answers, and there's a 45 for you, and I don't have a corresponding number, so I'll let you do that one as well. So hopefully you've done all the odd problems since you're done with the homework for this section, and then can't probably be ready to do another section because my videos are so long and dull that you'll just need you'll need a break from this. But we're a chunk of the way, at least we've made a start now. And so when you're motivated and ready, do the same thing for section 1.2. Watch the video. I'll explain what needs to be explained. I'll do an even problem and you'll do an odd problem. We'll just go through the whole course that way.